and I get the point. So this is in classical geometry how you know that you can reconstruct points from the sheaf. So that is good. And in the non-commutative geometry, it's another reason why sheaves are not too bad. You cannot really reconstruct points if you don't have them. If you have them, you can. But if you don't have them, you have to find some extra trick. Yeah. So as a conclusion for the commutative case, you can think of it like this. I have a spectrum, prime spectrum. I have structure sheaf, which actually comes from a representation choice. I choose representation functor, modules in the Zariski case. Graded modules, and then you have the graded Zariski case, a projective case. So this spectrum really contains the information about point-wise geometry. Because what I just explained, the points define things and the things define points. And then there's a very important step here, very fundamental, that the duality of commutative algebraic geometry and ring theory, if you want, commutative algebra, and which is mostly, there are many ways of saying this, but this very important way of saying is that there is a correspondence between the quasi-coherent sheaves on the variety, on the geometrical object. Quasi-coherent sheaves are sheaves that in some way follow from the ring. There are many ways of defining it, but it's a technical condition. And the quasi-coherent sheaves on X, they are just equivalent to the modules over the global sections. So that means that every quasi-coherent sheaf of modules over a ring, over the structure sheaf of a ring, so we take any quasi-coherent sheaf of modules, let's say, over the ring, then that comes from a structure sheaf, meaning that the global sections of this quasi-coherent sheaf are a module, such that the localization of that module gives you the quasi-coherent sheaf. So every quasi-coherent sheaf is a bunch of localizations. So if my philosophy is that the non-commutative geometry survives by taking a bunch of localizations over something like a topology, then I must have, if everything is to work, a version of Sear's theorem. Because I want that the algebra and the geometry are dual. Also in the non-commutative case.
They are what? I'm sorry, they are
dual. Dual, yeah. So this expresses, oh, there is a complete duality. Of course you can express in functoriality of spec and so on. But if you do that, there is a problem, because people begin to discuss the functoriality issues of spec, and even in the commutative case sometimes, but in the non-commutative case. And in fact, let me just say a few words. The functoriality of spec is an accident in the commutative case. It's a commutative accident. What is really going on is that spec itself can be viewed as a functor from rings to sheaves, to coherent sheaves. The spec takes an object to a sheaf. And if you view it like that, then a ring morphism between two, not necessarily commutative even, defines a natural transformation of the spec functor. And by accident, if the rings are commutative, that natural transformation just expresses a functoriality, but not always. So I think to present commutative algebraic geometry, it would be better to represent spec and not talk about functoriality in the beginning, but just say a ring morphism corresponds to a natural transformation of the spec functor. And then afterwards say, but look, commutativity forces that there is functoriality. But in my feeling, the property of being a natural transformation of the spec functor is more important. It's the essential thing. So therefore, this is a point that I always try to make for doing non-commutative geometry. It's not true that it's just a generalization of commutative geometry. You get more insight in certain structures, and even commutative geometers don't know so. For example, if you ask a commutative algebraic geometer what are really affine open sets, he will give you the definition. But why are those affine? Well, if you invert only one element, your affine algebra stays affine because you add one inverse. It stays a finitely generated algebra. That's one possible, but that's a linguistic answer, because the affinity of the algebra is defined by that in a sense. That's not true. The real reason is that the localization functor of an affine set is exact. The localizations are exact, like inverting one element is an exact functor. But there are localization ideals that are exact, and the ideal is not a principal ideal. So the exact functors correspond to the affine sets. That's exactly what is happening. And most commutative geometers don't know that. especially the direction from exactly implies F1. You have to prove that. So I want to say that even in computer geometry there are little details, maybe that's not so important, but nevertheless it's a fundamental understanding of what is going on in the geometry. That, for example, for me it's very important to know that if I look at exact functors, I'm really dealing with affine sets, even in a non-commutative sense. So that is the exact property that is fundamental. It's nothing to do with the localization being an affine algebra. Of course, by accident it's true. They chose the word affine to create confusion. Okay, so that's... So the Serre theorem is very important, and it will be necessary to have a Serre theorem in the non-commutative case. We have to remember that. I'm coming back to this. Because that's the proof of the pudding, and you know, the food cannot be copied. It's like Bob's eating habits. That's for later. Oh, if you instead of quasi-coherent say coherent, you get, instead of modules, finitely generated modules. The correspondence remains beautiful. So just point out that because in the non-commutative case I'm also very interested in the projective geometry for reasons of differential operators, and I will explain a little bit more than what's on the slides in a moment. But so there is a projective theory, of course, and you replace the category of modules by graded modules. But there is a very special localization there now. So the ring is positively graded then usually, and there is a positive part. So this, like, the ring plus is the positive part in the grading. So this positive part, in fact, is the ideal corresponding to the origin. But if you do projective geometry in some, let's say in some affine space, an+1, you remove this point and you take directions. So the removal of this point is in fact a localization. If you remove something in a variety, you localize at the ideal. So this ideal corresponding to it is the whole positive part. So if I want to remove this, I have to localize at this ideal. So it's not really the category of graded modules, it's the quotient category of graded modules for the top, which is called Proche by Grothendieck. So a projective variety is here somewhere, as in the cone, because it's up to homotopy. Right? So because it's up to homotopy, then you get here graded, and because you remove the top, you get this. So this is Proche. And this geometric space does not correspond nicely to the category of graded modules, but to the category of graded modules localized at that ideal. It's localized at the top. So you can express this again in that theory of, as I said, Grothendieck representation, the paper in Journal of K-theory. There's a second paper with Ndurusha and me, where we do the quotient of the representation, the quotients of representations, and the projective case is a quotient of the affine case. So now we are at the conclusion of the commutative situation, and then we want to go to the non-commutative geometry. And so what are we going to do? We have to do something about the topology, we have to do something about the localizations, and we have to do something about the spectrum. And if I want the point theory, I will have to invent some dynamical topology or geometry. Now this is perhaps very interesting for physics, because in my opinion, well, physics is about some kind of reality, and that's dynamic. And when you measure, you use time, and you use the dynamic of the system, even if you don't say so. So it's very logical, perhaps, to make a dynamical version of topology, and then construct some observation space. And maybe I can, instead of going linearly in the talk, I can show you, to wake you up again, I can show you the picture that at the end will result, to keep your appetite. So another thing I've thrown out of the talk is all the PowerPoint things. It's very, does it help if I turn it around?
Not much.
Not much.
If you keep it moving, it's fun.
Yeah, it gets worse.